I think we have a chance to grab another talk, an opening talk, which starts with introduction to graph machine learning. Okay, in front of us, Jakub Adamczyk and his talk about this topic. Without further ado, Jakub, the floor is yours. Please go ahead.
Okay, so hi everyone, I'm Jakub Adamczyk. I'm a data science engineer at Placewise, and I'm also a PhD candidate at HGH University of Krakow, where I focus on graph machine learning, on graph classification especially. So I wanted to do this in an introduction to graph machine learning. I think it's incredibly interesting. So let's get started with an introduction. Just a quick recap, what is a graph? I'm sure many of you know this very well because this is a well-researched topic. Taught at every computer science course, of course. So a graph is a mathematical object, an abstract representation, which can be implemented in different ways, but it's a representation, it's quite general. So we have some objects, some real life objects. Those may be people or atoms or cities in a road network, and they are represented as nodes or vertices in a graph, and we have some relations between them. For example, two people know each other, or someone follows someone on Twitter, or there is a road between cities, and those are edges or links between nodes. So we have a very general representation, some objects, some relations between them. And what is important is that in graphs, there's no order. Those are unordered sets. So we have a set of objects. There, for example, there's order to the people living in the world. This in contrast to, for example, text processing or image processing, where we have some order. For example, some words come before or after other words. On a graph, we only have relations between pairs of objects. So two objects either have an edge between them or not. And there are many different types of graphs. For example, there are directed graphs, where you can show the asymmetric relations. Because, for example, on Facebook, when you are friends with this is a symmetric relation. You either are friends or not. There is an edge or not. But for example, on Twitter, you follow someone. So there's a directed edge. You follow someone. This is asymmetric. Or those edges can be weighted. For example, if we have a road network and we have edge as a road between cities, then the length of that road may be a weight of an edge. And of course, nodes and edges can have features because we'll do machine learning on this. So we have features, feature vectors. For example, those nodes are people, we may know the user interests. Or for example, if we have atoms, we may have some physiochemical properties of atoms. The same for edges. For example, in a transaction graph where edges are transactions, we may know quite a bit about transactions. For example, when it happened. So this is one of the most general approaches to modeling. All in all, we can represent text, images, etc. also as particular types of graphs, because graphs are very general. You don't want to use the most general structure, but graphs are really convenient in constructing representations for many real-life relations. So let's see some examples. For example, road networks are natural graphs. They are processed as graphs, not necessarily even with machine learning. For example, in transportation, there are a lot of algorithms on graphs. We have social networks naturally, who knows whom, who follows whom. This is the basis of companies like Meta or Twitter to utilize graphs. We have knowledge graphs. For example, in medicine, we have diseases and their symptoms, how they are related to each other. We have chemical molecules, of course. Many drugs, well, most drugs have been designed using graph-based techniques, more or less, because molecules are graphs. We have drug-drug interactions, user-item interactions. Indeed, we have been using making recommender systems on graphs also for a very long time. We have computer networks, integrated circuits. So there's a lot of graphs in the natural world. They are very convenient to create, to represent our data. And as I said, in practice, most real-world graphs are attributed because we don't only have the graph structure, we also have some knowledge about those objects that are represented on a graph. So we have two sources of information here. We have graph topology, or its structure. So what are the nodes? Which nodes are connected by an edge, so what objects have a relation, and this is a graph topology or structure. It is typically defined using adjacency matrix. On this graphic here, this is the adjacency matrix, n times n, when you have n nodes, and there is one if nodes I and J are connected by an edge. Those, of course, can be also weights. This can be symmetric, asymmetric, but this way you can easily, with a single matrix, define what objects have relations with each other. So this is the graph structure is the first source of information. Obviously, we can have molecules or social networks with different structures. And we also have nodes and edge features. So those, for example, feature vectors of users, if they are nodes, like their interests, or for example, atomic features, or those, if we have a transaction graph, we may have whole vectors of features for our edges. So this is the second source of information. This is the feature matrix, or two feature matrices for nodes and for edges. And in graph machine learning, we want to utilize both of them. We want to use both the topology, because it provides information about and also about our features, because in all machine learning we want to use features because they describe our objects. And this means that graph machine learning will always require some feature engineering. Even if you use neural networks, graph neural networks, no matter what you do, you will need to do this feature engineering. This is in contrast, for example, to images or text, where you just put text for text classification, or you just do image classification using the object itself. Here you will need engineering for your objects represented as nodes. And this feature engineering utilizes either domain-specific features, like for example, you just do regular feature engineering, you extract feature vectors, and also you can add some features based on this adjacency matrix. You can extract features from the graph itself using graph theory, so-called graph descriptors. There are lots of them, whole books about it, like centrality measures, random walks, and others. There's a lot of different graph descriptors that can add interesting features matrix based on the structure of the graph. So once we have the graph structure, once we have the graph features, for example, we have chemical molecules, they are very easily constructed this way. Then we can go into machine learning. So what we can do in this graph machine learning, let's see some applications. Firstly, we can do graph classification. So we want to classify the whole graph. For example, if it's a whole chemical molecule, we want to know whether the molecule is toxic or not, or for example, whether a new drug will be active against a disease or not. So this is molecular property prediction, or we can do protein function prediction, because proteins are often of interest in bioinformatics. So this is typically used in bio and chemoinformatics in pharmaceutical applications. For example, in Pfizer, Bayer, Moderna, they all do ADMET, properties prediction in chemistry. There are whole new companies like Benevolent AI that are doing completely AI generated drugs. They are currently undergoing clinical trials. So incredibly interesting application of graph machine learning. And typical methods in graph classification, especially in molecules, as I say, those are either molecular fingerprints. Molecular fingerprints are algorithms for graph vectorization or graph embedding. You may hear about them at my colleague's presentation at the VOD section, or we can use graph neural networks, which are pretty general. We will delve into them in just a minute. And we can also do node classification, where you want to classify a node, a single vertex inside a graph, typically very large graph, like a whole social network or the whole transaction network. And typical applications here are, for example, tagging posts, movies, products, etc., any objects that are inside your graph. Because, for example, posts and movies and reviews may be connected to each other, so they form a graph. We can do the fake news detection, the fraud detection, etc., using the graph of objects. Of course, this can be done as tabular classification, as you may very well know. For example, fraud detection can be done just using classical tabular learning. But if you additionally use the graph information, so you do node classification instead of just tabular classification, your performance may be much better because you explicitly leverage this additional information that is inside a graph. And for example, there are commercial applications. For example, travel time at Google Maps actually uses node regression to predict the travel time. If you at Google Maps search for travel time between points A and B, it actually does a node regression. It does a regression on road segments. Each road segment is a node in a graph. And Google Maps just does a regression on all those road segments between points A and B. So a great application. And also AWS, for example, uses graph neural networks for and node classification specifically for fraud detection. They help clients to do this, for example, using their Neptune graph database. So definitely there are commercial applications of this already. And typical methods for node classification are either random walk based, for example, node2vec or deep walk. You may recall this from computer science studies because those are pretty old methods, but still very good in practice, or graph neural networks, which are definitely state-of-the-art in terms of node classification. Also do link prediction. Link prediction wants to add new edges inside a graph. You have a graph, for example, interactions between users and items, or who knows whom on Facebook, and you want to suggest new edges. For example, you think that two people reasonably should know each other, so you suggest an edge. You recommend a new friend. Link prediction is basically what recommender systems do, because in recommender systems you want to suggest that user buy an item. So you want to create a new edge between user and an item inside the graph. And in fact, currently the state-of-the-art solutions on all conferences in terms of machine learning research are link prediction on graphs. So graph neural networks for recommender systems are really powerful. They can also do interaction prediction, for example, drug-drug or protein-protein interaction prediction. There are a lot of commercial examples of this. For example, Pinterest, Uber Eats, Alibaba, Snapchat, they all have papers and blog posts and commercial applications of graph neural networks for recommendation. They're really convenient in terms of deployment and operations also. And typical methods for link prediction are either neighbor indices. For example, PageRank is famous for link prediction as a neighbor index, or a graph neural network, of course, can also be applied. So I mentioned graph neural networks a few times. So let's get a bit deeper into them, because they are not the only solution for learning on graphs. They are often maybe not even the best solution, but they are the most general. You can learn them, how they work, and you can apply them in many different contexts. So the basic idea behind a graph neural network is pretty similar to what we may know from, for example, from CNNs. You have a standard architecture where you have feed-forward layers, you have nonlinear activation, and you output some embeddings. So you have an input, process it with different layers, and then you output some embedding, just like with images. But here, this will be based on a notion of so-called message passing between a neighboring nodes. And via this message passing, which we will define in just a minute, between neighbors, we can perform graph convolution, because this will be graph convolutional networks typically. And here we will process actually node embeddings. Okay, so the basic unit which is processed by graph neural networks are nodes. The graph structure will be, of course, used to define how message passing is done, but the basic unit, what we start with, are node features, which are the initial embedding of our nodes, and then we will learn the reasonable node representations inside some space, and those will be node embeddings. So let's see concretely how this works. We have the message passing. So we have an input graph, and in a given layer, remember that initially we start with some graph. By the way, the graph structure will not be modified. What we will be learning are node embeddings, the vectors of features of each node. So we start with some initial features, which we feature engineered, as I said before, and in a given layer, each node will perform a message passing. And those messages are really just neighbors feature vectors. So when you have a node and you have its neighbors, so nodes connected to it via an edge, a node receives messages or just feature vectors from all its neighbors. So for example, if a user knows other users, it receives all those features vectors from the user that he knows. And those neighbor vectors are then aggregated into a single vector representing the whole neighborhood. The reason is that nodes can have a different number of neighbors. For example, one user may buy a lot, so have a lot of neighbors inside a user item graph, whereas other may buy very few items. So nodes have different number of neighbors, and then we aggregate all of those neighbors with a typically very simple function, for example, via a simple mean or sum, into a single message representing the neighborhood. Okay, so we take all the messages from our neighbors. For example, we calculate a mean, and this is the average, for example, neighborhood. This is what is contained inside our neighborhood. And then we take the single vector, single message from our neighbors and the node itself, what it knows so far, and then we update it. We combine the new knowledge from our neighbors with the node itself, what we know about it. Of course, initially those will be all feature vectors, then those will be in further layers node embeddings, but then we update this node embedding with our neighbors, and then we update it. For example, this can also be a simple mean again, and then we update our embedding, and then this new node embedding is our hidden representation, the first node embedding, and then we can apply nonlinear activation function, typically ReLU activation on this, and then we go to the next layer. And this aggregate and update functions are actually what defines graph convolution. Because this message exchange, when you get vectors of your neighbors and you update yourself with this information, this way you gain information from your neighbors. So a node in the first layer, at the beginning it knew only about itself. After the first layer, it knows about its neighbors. But then again, remember that this message passing is done for each and every node in a given layer. So every node learns about its direct neighbors, the nodes that are connected to it. So if you do this 2 times, so you stack 2 layers on top of each other, then a node gains information not only from its direct neighbors, but from their neighbors also. So if you stack k layers, you gain information from a so-called k-hop neighborhood. So from the nodes k hops or edges from you. So you gain information from a larger part of the graph. And different GNNs differ in how to aggregate those messages from the neighbors in each layer and how to update the node with new information. So we have the aggregate and combine functions. And this way, by choosing different functions, we can define different graph convolutions. Because in contrast to, for example, convolutional networks on images, on graphs, convolution is not a single unique convolution. There are many different convolutions on graphs, and in fact, different GNNs, different graph neural networks, define different graph convolutions. So let's see some examples. For example, graph convolutional network, the first really successful GNN, works in a following way. The aggregate function, how to combine all the neighbors inside a single vector, is just a simple mean. So you just take a mean of your neighbors, and then you take in the combine operation, where you use the neighbors to update the node itself, you take this average vector of your neighbors, and then you average with the node itself. So you take mean of neighbors and then the mean of the new data and the node itself. This is incredibly simple. Also in code, it's incredibly simple because just mean 2 times. And this can be applied to anything. To node classification, graph classification, link prediction. This is, in fact, despite this simplicity, often state-of-the-art solution. And on the other hand, Graph Sage proposed to aggregate the neighbors of a simple mean, but to update the node with this new information from the neighbors, of mean vector from the neighbors, in a slightly more interesting way, because they propose to concatenate or just glue together 2 vectors, the node itself and the mean vector of from the neighbors, and then to combine them not with a simple mean, but with a linear projection. Linear projection is just a matrix multiplication. You add a weight matrix to keep the dimensionality the same, because remember, concatenation, that is combining 2 vectors together, increases dimensionality 2 times. So if you do linear projection or matrix multiplication, you will reduce the dimensionality to keep it the same. Okay, so this way, Graph Sage can focus more on the node itself Okay, so because this way, if then your initial features were very good, if the node itself knows a lot, it doesn't need the neighbors really, it can be preserved this way. But it's still incredibly simple, just some additional weights in terms of one matrix. This can also be applied to anything. It often gives really good results. We have also graph attention network because, of course, someone tried to add attention here. And we can have attention weighted sum of the neighbors and the node. So the node attends to itself and to all its neighbors, and then it uses the attention weighted sum, because attention is really here a weighted convolution. Attention is a way to weight the convolution of your neighbors. And this G18 is often applied to node classification, because this weighting of neighbors can be really beneficial for node classification. And graph isomorphism network, GIN, is applied to graph classification, and they proposed to take a sum of neighbors instead of mean. This may seem very similar, but it leads to slightly different theoretical properties. And they propose to combine the neighbors, the vector from the neighbors, with the node itself with a two-layer MLP. This is similar to, for example, what transformers do, because transformers use two-layer MLPs inside. And GIN is really good for graph classification. And those four convolutions are defined with different aggregate and combine functions, and they are really different GNNs. So if you read the paper about GNNs, really look for aggregate and combine definitions. They will be there in some form. And via different aggregate and combine definitions, we create different GNNs. Okay. So how to apply those in practice for node graph and classification and link prediction? So for node classification, it's actually incredibly simple, because those message passing layers just output embeddings, right? Because after each message passing layer, we have an embedding for each node. So if we have node embeddings, we can simply classify them. We take a node embedding and we classify it with a linear layer, with a softmax, just a regular classifier for neural networks. Okay, so this is the simplest way. You just use MLP on node embeddings. And there are two ways to evaluate this approach in practice: the transductive and inductive approaches. The transductive approach, used often in papers, works in a way that test nodes are included in your training graph. So you take all the nodes, training, validation, test nodes, and their initial features. You do message passing on everything, but you use labels only from the training set. So the test features are used in a transductive setting, but not the test labels for training the network. This may sound pretty weird in terms of practical testing and deployment of models. So we have also an inductive setting, which I think may be more intuitive, where the test nodes are just completely missing from your training graph. You train only on the training graph, then you add new test nodes, and only then you do the testing. This is called inductive setting, and this is maybe more natural. And popular architectures for node classification are, as I said, GCN, graph session, GAT, but also something called simplified graph convolution and spectral simplified graph convolution, SGC and SSGC, are simplified GNNs, are even more simplified because they remove the activation function. This may sound crazy because we all know we need activation functions, but nevertheless, SGC proposed to take basically GCN and remove the activation function. Okay, so that's just use linear activation, and surprisingly, this works. This works really well, in fact. And of course, it's much faster, much easier to train. So they have very good papers, of course, so I encourage you to read them. But yeah, those also work well for node classification. For graph classification, on the other hand, we have a slight problem because we have node embeddings, but now we want to classify the whole graph. So we need a single vector to represent the whole graph. We need a graph embedding. And this is done via a so-called readout function. So we take node embeddings, we put them into one matrix, we stack node embeddings as rows in a matrix, and then we take, for example, mean or max or sum or some other simple functions of our columns. This way, no matter how many nodes there were in a graph, for example, if you had small or large molecule, if you take node embeddings as rows and you take, for example, mean of each feature of each column, then you finally have a single vector for the whole graph. This, of course, only inductive because you care about predicting new graphs, so you care about classifying new graphs. And popular architectures are GCN, GraphSage, GIN, and also something called principal neighborhood aggregation. Pretty interesting paper, also very well written. I encourage you to read it for graph classification. But yeah, the basic idea is very, very similar to node classification. We just need this extra readout step. And last but not least, the link prediction. Because in link prediction, we want to operate on pairs of nodes, right? Because there's an edge between two nodes. So, and we have node embeddings of single nodes. So we have to operate on pairs of nodes. And this works as follows. We translated the problem into a binary classification. So you take the existing edges that are inside your graph, inside your training graph, and you take them as a real edges, as a class 1. Those edges are really there in your graph. And then you add fake edges. You create artificial edges that are not in your graph. They are fake edges, they are class 0. This is something similar to, for example, contrastive learning or self-supervised learning, where you create like fake or corrupted things as a negative class. So here you create the fake edges. And then you want to learn node embeddings in such a way that the probability of a real edge existing will be as high as possible, and the probability of fake edge existing will be minimized. So you want your network to learn which node embeddings should have an edge between them. And we will measure similarity between node embeddings for this. If you have two vectors, so two node embeddings, the simplest way to measure similarity is just to take a dot product, because dot product between two vectors will be high if those vectors are similar. And then if you take a dot product, which results in just a single number, and you put it through the sigmoid function, you have a probability between 0 and 1. This is probability of edge existing. Okay, so to do this dot product between node embeddings, then the sigmoid, you have probability, and you want to do maximize this probability for real edges and minimize this probability for your added fake edges. And popular architectures for this are GCN and GraphSage, and also, again, simplified networks like SEAL or Light GCN, which is, again, very simplified GCN. Because really on graphs, we want to do simple algorithms. They work really well. Okay, so we know now how to apply GNNs for those 3 types of supervised learning problems. And I want to share with you some tips and tricks in terms of learning and designing GNNs that come from my experience. And typically, you want to start with very shallow networks. GNNs are often best when they are very small. 2 or 3 layers are often totally enough. So for example, just 2 or 3 convolutions on top of each other. This is because on the graphs, relations are often short. You often have everything that you need, for example, for node classification, very close to the node itself. So you don't need many layers, because many layers just mean you look further in a graph. You often don't need this. 2 or 3 layers are totally enough in many cases. Max about 10, 20 layers for incredibly hard problems, but this is max, you don't need absolutely anymore. Start small, and also start simple. Use simplified models like SGC or Light GCN or whatever in your domain. Look for simple models, because simple models are much more stable to train on graphs, much faster, they often are much less prone to overfitting. So start with small, simple models on graphs. This is also a large advantage because models on graphs are often cheap to train. Also add topological features. There are things like Laplacian positional encoding, LabPE, or node-to-vec vectors. You can add topological features to your feature vectors of nodes. there are many papers, a lot of papers in this area that show that modifying not the architecture of GNN, but rather the features is much more beneficial. And also, there are a few well-known architecture tricks like jumping knowledge, basically a lot of skip connections. Jumping knowledge is really great, and virtual node technique, and also a flag technique, which makes the networks more robust against adversarial attacks, and also does a bit of data augmentation. So those three architecture tricks often improve your basic network a lot. Pooling because in CNNs, in computer vision, we do pooling, right? On graphs, graph pooling doesn't really work yet. There are many papers for graph pooling, and most of them don't really work. And pre-training models for graphs is really, really hard. Pre-trained models often do not exist or do not work very well. Maybe in chemistry, something works. But other than chemistry, really pre-trained models are non-existent or do not work. You train from scratch, so start with small, simple models. And there are other graph learning approaches, of course. We have graph transformers, of course, random walks, as I said, neighbor indices. We also have graph embedding algorithms like graph autoencoders. So there's a whole world of graph machine learning. It's incredibly interesting for various problems. I absolutely encourage you to read about it. So this is the end of my talk. Thank you for your attention. Please ask questions. Please rate the talk. You have a QR code here. So yeah, I'm happy to receive questions.
Okay, from the very beginning, Jakub, it was a great talk. Well, congratulations. It was outstanding. And referencing the questions, I've got one question from the chat, and I've put it on the wall on Slido. And the question sounds like this: do all of the nodes have to be of the same type of objects? What if I want to do some analysis where my nodes are persons, companies, and addresses? Edges are relationships between them?
Okay, this is a great question. So actually, I want to go to the beginning of the presentation because actually I didn't mention all the types of graphs here, because there's those graphs that I mentioned are most of them are so-called homogeneous graph, where we have this only one type of node, for example, only people. But for example, we have a heterogeneous graphs. For example, for user item interactions, actually we have two types of nodes. We have user nodes and item nodes. So we can absolutely have heterogeneous graphs and graph neural networks for heterogeneous graphs. Link prediction is often done on heterogeneous graphs. For example, if you read the Light GCN paper, it has a nice introduction to learning on heterogeneous graphs.
Thank you very much. We do all understand, but we have just finished the time that has been allocated for this talk. If you would like to contact Jakub, I think it will be possible after the conference. Again, thank you for this presentation. It was very, very good. Thank you very much. And I thank you all for listening. And please do not forget to rate this presentation. In a moment, at 5:15, we're going to begin the last presentation, which is allocated in the agenda for the day 1 of today's conference. Thank you very much and see you soon. Bye-bye.